Hi everyone, we're going to cover section 4.4 and 4.5 today. We're going to discuss the real zeros of polynomial functions, also known as x-intercepts, and the fundamental theorem of algebra. So as you can see, we have a lot of learning objectives today. We're going to understand the factor theorem, factor higher degree polynomials, analyze polynomials having multiple zeros, solve higher degree polynomial equations, understand the rational zeros test, apply the fundamental theorem of algebra, factor polynomials having complex zeros, and solve polynomial equations having complex solutions. So this first page is just a bunch of notes with some good information here. Characteristics of the zeros of a polynomial. And remember, just a reminder, the word zeros is just another word for the x-intercepts. Sometimes it's also called the roots or the solutions. The factor theorem says if k is a zero of a polynomial, then x minus k is a factor of the polynomial. And we've sort of used that information in reverse already. When we set a polynomial equation equal to 0 and we factor it, we used something called the zero product principle. Or maybe we called it the principle of zero products. If you have factors multiplied together, and that's what a factor is something multiplied with something else. If you have factors, things multiplied, and they equal 0, that must mean that one of the factors is equal to 0. So we've used this earlier. When we factored, we might have something like this, x minus some number. We would set it equal to 0 and solve. And of course, if you have x minus k equals 0, and then you add k to each side to solve for x, you get x is equal to k. So if k is a 0, or an x-intercept, or a root, or a solution, then x minus k is a factor. So that's what the factor theorem is saying. And as I said, we've already really used the converse of that statement already, where we switch the if and then part. Now, the fundamental theorem of algebra is an extension of that. It says a polynomial of degree n can be written as a sub n times x minus k sub 1 times x minus k sub 2 ... times x minus k sub n. So we know that if you have a polynomial of degree n, there can be at most n different zeros or x-intercepts. And so there would be n of these factors. So you could take all of the solutions and write them as factors. Now a sub n is just the leading coefficient. So for example, if I had a polynomial that was 7x to the third power plus 2x squared minus x plus 10. The leading coefficient is 7, so that's what a sub n is referring to. Whatever the coefficient is of the term with the nth degree. This would be a third degree polynomial. So I know I'm going into a lot of explanation just to remind you how this all kind of fits together. So the k's, k sub 1, k sub 2, k sub 3, all the way to k sub whatever, are the zeros. They might be real numbers, they might be complex numbers, and they're all factors or zeros of the polynomial. It is possible that a zero is repeated. So for example, you might have k sub I and k sub j, or maybe to put it in numerical terms, let's say the third and the fourth factors or zeros are the same number. So sometimes that happens. Sometimes you have zeros that repeat. Okay, this means that a polynomial of degree n has n zeros, real or complex, of which one or more may be repeated. In other words, you may have the same factor twice. For example, if I factored something and I wrote x minus 3 squared, well, that means x minus 3 is a factor twice. Okay, that's what is meant by repeated. Now, the number of times a factor occurs in the completed factorization of a polynomial is called the multiplicity of the zero. So this one over here would have a multiplicity of 2 because it is listed twice. If the multiplicity of a zero is even, then the graph of the polynomial is tangent to the x-axis at x equals k. So let me draw you a little picture of what that would look like. Think about our x squared friends, our quadratic functions. Quadratic functions, when we graph them, look like a parabola. If you had a factor repeating, such as this example over here, then at x equals 3, what would happen is the graph would be tangent there. So it would look something like this. The graph would just touch the x-axis at that point. I like to think of it as kind of bouncing off of the x-axis. It doesn't actually cross the x-axis there. It just touches the x-axis at that one point. And that's what we mean by tangent to the graph. And that happens anytime your multiplicity is an even number. 2, 4, 6, 8, etc. If the multiplicity is odd, then the graph of the polynomial simply crosses the x-axis at x equals k. So if I didn't have a multiplicity of 2, if it was just x minus 3, then at 3, it would simply cross the x-axis in some way. Now, the higher the multiplicity, the more the curve flattens out near 0. So sometimes it may actually kind of curve. I wonder if I have a graph open. Yes, maybe we can observe that here. So let me move this. So if I have y equals x to the power of, let's say, 3, an odd number, we can see how it sort of, when it crosses the x-axis, it sort of flattens out. If I make that degree even higher, y equals x to the power of, say, 5, it flattens out even more. 7, 9, so you see how the greater the degree, it is just more flat where it crosses the x-axis. So that's kind of interesting. So the big idea here is, if it is an even multiplicity, if the factor appears an even number of times, 2, 4, 6, 8, then at that 0, the graph will be tangent to that point. If the multiplicity is odd, then in some way, the graph will simply cross the x-axis at that point. All right, a lot of information on this page. All right, this is an interesting thing about complex zeros. Complex zeros always appear in pairs, kind of like teenage girls going to the restroom, okay? If you have a plus bi as a 0, guess what? A minus bi will also be a 0. We call those complex conjugates. So we talked earlier about conjugates. Complex conjugates are two complex numbers with different signs in the middle. A plus bi, a minus bi. All right, so another fact, probably the most complicated part of this lesson, is something called the rational zeros test. If we're trying to solve a polynomial of a higher degree, this is a method that is used to find the zero when factoring is not feasible. If we have just a quadratic or sometimes a cubic or maybe even a quartic function, sometimes factoring can be really nice. But if we can't factor the polynomial, the rational zeros test is a way. Sometimes it can be a little bit long, tedious process, but the idea is to find all possible ratios P over Q, where P is a factor of A naught and Q is a factor of A sub n. What in the world does that mean? Well, A sub 0 is going to be the constant of your polynomial equation or function, and A sub n is the leading coefficient. So I wrote a polynomial earlier. Let me see. Give you an example. I'll just write it down here. We had something like 7x to the third plus 2x squared minus x plus 10, I think I said. So P are all the factors of 10. The constant, that's A sub 0. So let's see, the factors of 10 are 1, 2, 5, and 10. And we could actually say plus or minus because we could have negatives. Now the factors of 7, that's A sub n, that's where your Q's come from your leading coefficient. And of course that's assuming that everything is in order. The factors of 7 aren't so many. It's just plus or minus 1 and plus or minus 7. So to find all the P's over Q's, we take all of these numbers divided by all of these numbers. So that's quite a lot of possibilities. So I like to just do this very systematically. I'll start with 1 as my numerator. 1 over 1. 1 over 7. And then I'll move to 2. 2 over 1 and 2 over 7. And then I'll move to 5. 5 over 1, 5 over 7. And finally, I'll move to 10. 10 over 1 and 10 over 7. Again, plus or minus. Now, I want to simplify these if I can. So 1 over 1 is just 1. 1/7 I'll just keep. 2 over 1 is just 2. 2/7. 5 over 1 is just 5. 5/7. 10 and 10/7. So actually that's 1, 2, 3, 4, 5, 6, 7, 8. It's actually 16 possibilities if you consider that the numbers could be positive or negative. So what this is saying is out of these 16 numbers, you will find the 3 rational zeros. Okay, if this crosses the x-axis at a nice place, a rational number is a number that can be written as a ratio, such as these, then we will find the 3 of those among these 16. And so then you've narrowed it down from an infinite number of possibilities to just 16, so that's something. And then we can test out the ones that work using synthetic division or long division or some other way. If we are given a complex zero of a polynomial, so I'm reading right here now, we may find another zero using complex conjugate of the given zero. So in other words, if I know that 3 plus 4i is a zero, then I also know 3 minus 4i is a zero. If I know that, if I know something about a complex zero, then I can take the complex number and its conjugate, multiply them together, and then use long division to further break this down into factors. Now this page had a lot of information. We are now going to do some examples utilizing all of this information. So I hope you're still with me. All right, so first it says list the factors of the polynomial graphed below. Okay, so we're going to use the first thing that we talked about in our notes, which was the factor theorem. So I'm going to first find the zeros, which is very easy on a graph like this. I see that it crosses the x-axis at -3 and 0 and 1. So x equals -3, x equals 0, and x equals 1 are my 3 zeros. Now I can turn these into factors. Think about taking this first equation and adding 3 to each side. If you add 3 to each side, you'll get x plus 3 equals 0. Now x equals 0 I'm going to keep because it already says equals 0. And the last one, I'll subtract 1 from each side. So I want each factor to say equals 0. So these are my 3 factors. X plus 3 is a factor, x is a factor, and x minus 1 is a factor. So this function, whatever it is, in factored form would be x plus 3 and x, and I would probably put the x in front like this, and x minus 1. So this is the polynomial function graphed here. I could multiply that all out if I wanted to and get this in standard form. It didn't ask me to do that, but just so you see, if I multiply these two binomials together, I'll just let the x hang out for a while. I'll do x times x is x squared. X times -1 is -x. 3 times x is 3x. And 3 times -1 is -3. Combining my like terms, minus 1x plus 3x is plus 2x. Then I could distribute the x to each of these. So I'd get x cubed plus 2x squared minus 3x. So this would be the polynomial in standard form. So kind of interesting. You can use the zeros to find the factors and then use the factors to find the polynomial in standard form. I think it's kind of neat. So again, this is a 3rd degree polynomial. I know that because the highest power of x is 3. And notice there are 3 zeros. I know there will never be more zeros than the highest power of x. Number 2 says use the given zeros to write the complete factored form of f of x. Okay, so this is an x squared. So I know there's only 2 zeros, and there they are, -6 and 5/2. So I know that x is equal to -6 and x is equal to 5/2. I want to turn these into factors. For the one on the left, I'm just going to add 6 to each side. And once it says equals 0, we're good to go. Now, I really don't want fractions in my factors, and I can take care of that if I just multiply both sides by 2. Then what I have is 2x equals 5. And then I can subtract 5 from each side, and I have a lovely factor. One of my factors is x plus 6. The other factor is 2x minus 5. So knowing the zeros is can be used as a shortcut for factoring, or at least a different way to factor. Now, if I were to multiply these back out, I would get 2x squared, so x times 2x is 2x squared. X times minus 5 is minus 5x. 6 times 2x is 12x. And 6 times minus 5 is minus 30. That would give me 2x squared. And then when I combine these, that will give me 7x minus 30. Why is that not the same as my original function? How is this different from my original function? This function actually needs to be multiplied by 3. If I multiply it by 3, I will get 6x squared plus 21x minus 90. And so I need to throw in here a leading coefficient of 3. In other words, the 3 has been factored out before the factoring began. I almost forgot about that part. Number 3 says use the graph to factor f of x. So f of x is shown, and it's it's a 4th degree polynomial. So I can expect at the most 4 zeros, and I see that there are 4 zeros. One right here, 1, 2, 3, 4. And it looks like this graph is scaled along the x-axis at least by 2's. So this one right here is going to be x equals -2. And then this one looks like it's between 0 and 2, so I'm going to call that x equals 1. And then I've got one between 2 and 4. I'm going to call that x equals 3. And then I have one at x equals 4. So those are my 4 zeros. If I turn those into factors, I will add 2 to each side to get that equal to 0. So one of my factors is x plus 2. I'll subtract 1. So one of my factors is x minus 1. I'll subtract 3 on this one. And I'll subtract 4 on this one. And so the factored version, and I can put these factors in any order, it doesn't matter. X plus 2, x minus 1, x minus 3, and x minus 4. Now so far we've still only seen polynomials where each of the factors has a multiplicity of 1, where none of these factors are repeating. But don't worry, those examples are coming up shortly. Hello. The page is loading very slowly. Just giving it a second to think about its life's choices. I don't know why that's not loading. Well, I don't know why it's not loading. Let me see here. Well, I apologize for this delay. I'm not really sure what's going on. Let me try to, let's see. Try to reopen it. Oh, sorry about that. We are, looks like we are in business. Okay. Oh, crisis averted. Sorry about the delay. Okay, we're writing the polynomials in complete factored form given that the leading coefficient is either 1 or -1. Okay, that's nice because that a couple of examples ago, I had a little bit of a problem with, I had some factors and I had to multiply by 3 and I didn't quite figure that out. So anyways, that way I don't have to worry about, oh, has something been factored out? I can just take the factors and run with it. So let's see what the zeros are. I see there's a 0 here, here, and here. And these are scaled by 1s along the x-axis. So let's see, -1, 2, 3, 4. So I have x equals -4 as one of my zeros. It looks like x equals -1 and x equals 3. All with a multiplicity of 1, none of them repeat. I'll add 4 to each side to find my first factor of x plus 4. Add 1 to get x plus 1 is a factor, and subtract 3. So again, notice that whatever your 0 is, you have the opposite sign in your factor. That's really important to keep in mind. Now, we talked about, I believe, that when your leading coefficient, when you have an odd degreed function, your ends point in different directions. So this is as we would expect. And you can tell what the right side does by the leading coefficient. And we're supposed to decide if the leading coefficient is 1 or -1, and that's how I tell. Look at your right end. Your right end is pointing down. So I know the leading coefficient is a -1. And then I can put my factors, x plus 4, x plus 1, and x minus 3 in any order. Now often when we write a function and the leading coefficient is -1, we mathematicians get a little bit lazy and we don't always put the 1. It might just be a negative sign. Know that these two mean the same thing. When I look at the next example, I see that both ends are pointing up. That tells me a couple of things. It tells me that this is an even degreed polynomial, since both ends point in the same direction. And it tells me that this time the leading coefficient will be +1, since the right end is pointing up. Let's look at the zeros. I've got a 0 here, 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 and here. So this is a 4th degree polynomial. And it looks like the x-axis is scaled by 2s. So let's see, -2, -4, -5 is 1, 0. -2, +1, and +3 appear to be my zeros. So my factors are x plus 5, x plus 2, x minus 1, and x minus 3. And of course, those would all say equals 0. And so when I put them together, I remember the leading coefficient is 1, so I could put a 1 here or not. It's understood if I don't write it that the leading coefficient is going to be 1. And so this is the factored form of this particular function. Okay. For number 5, it says write the polynomials in complete factored form The leading coefficient is not plus or minus 1, so we're going to need to use a point on the graph to solve for the leading coefficient. Okay, so we begin with our zeros. Let's see, the x-axis is scaled by ones, so I have x equals -3. I have x equals -2. I have x equals -1. And I have x equals +1. And all of those are multiplicity of 1, so this is a 4th degree. I want you to notice that both ends are pointing down. So I know my leading coefficient is negative. I just don't know what it is exactly. So when I write my function, what I can do is whatever the leading coefficient is, I'm just going to call it a for now. And my factors are, I didn't write that part, but if I have x equals -3, the factor is x plus 3. And if I have x equals -2, the factor is x plus 2. And then the next one would be x plus 1, and then x minus 1. Remember, the sign inside the factor is always the opposite of the sign of the 0. So to solve for a, I can find another point on the graph. If I can use the y-intercept, I like to, because the y-intercept has an x value of 0, and this y value is 2. So I'm going to use the point 0, 2. So here's what I know. If I plug in 0, then the answer is going to be 2. So let me take this and plug in 0 everywhere I see an x. And I know that's going to equal 2. Let's simplify. So I have 0 plus 3 is 3, 0 plus 2 is 2, 0 plus 1 is 1, and 0 minus 1 is -1. So now let me multiply all of these together. That's going to be -6, I believe. So -6 times a, I'll write like this, equals 2. I can divide both sides by -6. And a is, I reduce that fraction, -1/3. So I can go back here to where I had a, and I could rewrite this. But now that I know a is -1/3, I'll say f of x equals -1/3 times x plus 3 times x plus 2 times x plus 1 times x minus 1. And there you have it. Now, I didn't leave a lot of room for the next problem, but the next problem is very similar. It also has 4 zeros, but this time I see that the ends are pointing up, so I'm expecting my a value to be positive this time. So it crosses the x-axis here, 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 and here. And it looks like we are scaling by 2's. So I've got x equals -4, x equals 0, x equals 2, and x equals 4. So my factors are going to be whatever, I don't know my a value yet, but it'll be x plus 4, x, normally I would put that in the front, but I'll just put it there for now, x minus 2, and x minus 4. Now, to figure out a, I need to find another point on this graph. Maybe I will use this point right here, which appears to be 1, 1. That seems pretty nice. 0, 0 is not going to work because anything would work for a in that case. So I'm going to plug in 1. So if I plug in 1 for x, then the answer should also be 1. So let's see, if I put a 1 everywhere, that's going to say a times 1 plus 4 times 1 times 1 minus 2 times 1 minus 4, and the answer should equal 1. So let's see, 1 plus 4 is 5, 1, 1 minus 2 is negative 1, and 1 minus 4 is negative 3. Let's simplify by multiplying all of these numbers together. I think that's going to be positive 15. So let me come over here. I've got 15 times a equals 1. Dividing both sides by 15, I get a is 1/15. So my answer is f of x equals 1/15, and then my factors. Now I'm going to put x in front this time because that's normally what I would do. If it's just an x by itself, put it in front with the 1/15. And I didn't write that very neatly. Let me clean it up a little bit. There we go. All right, lots of examples today. Write the complete factored form of f of x equals blah, 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 given that k equals 3/7 is a 0. That looks like a rational number to me. So I think we are going to, I think what we're going to do is, I know what we're going to do. We're going to graph this. Trying to figure out what did they want us to do. They want us to graph this one. This would be one where if this was a test question, I would actually give you this graph. So let's see. It's y equals 35x to the power of 4 plus 48x cubed minus 41x squared plus 6x. All right, so here's the deal. You can look at this and see where it crosses the x-axis. It crosses the x-axis at -2. It crosses the x-axis at 0. And by the way, since this is a 4th degree polynomial, I expect it to cross the x-axis no more than 4 times. And guess what? It crosses 4 times. Once at -2, once at 0, once at 0.2, and once at this number. This is why they told me that 3/7 is a 0, because I know now that that's the number that's 3/7. Okay, so I've got 3/7, and these are so close together, I've got to, that's 3/7, that's 0.2, that's -2, and then of course 0. So let me go back to my notes now and see what I can do with this information. So I know that x equals 3/7 was one of my zeros. I had x equals -2. I had x equals 0. And I also had x equals 0.2. Now, for this one, I'm going to multiply both sides by 7 first, because multiplying by 7 gets rid of that divided by 7. That leaves me with 7x equals 3. I'll subtract 3 from each side, because you want your factors to be nice numbers, not fractions or decimals. So there's one of my factors. This one I can just add 2 to each side. That's lovely. There's another factor. X equals 0 is already good. Now for 0.2 as a fraction is 1/5. So I can multiply both sides by 5 and get 5x equals 1. subtract 1 from each side, and I have a lovely factor of 5x minus 1. Now, notice that my leading coefficient is 35. Notice that I have a 7 and a 5 in the front of two factors, and 7 times 5 is 35. So I know that my leading coefficient is just going to be 35. No different, and that's going to be taken care of with the 7 and the 5. Now this one that says x equals 0, I'm going to start with that factor. I'm just going to put x. And then I can put my others in whatever order you want. Doesn't matter. So if you were to multiply all of these out, you would get this original function. I know that at some point I would be multiplying 7 times 5, which is where the 35 comes from. So this is the factored version using these zeros. All right, now we're getting into multiplicities. Lots of examples here. It says identify the zero and the multiplicity of each zero of the polynomial, then identify the degree of each polynomial. Use Desmos.com to graph each polynomial to observe the behavior of the graph at each zero and to justify the end behavior of each graph. Okay, let's take a look at the factors of g of x. The first factor is 3, but that's not a variable, so I'm going to ignore that. And then I see x. Okay, the fact that it says x tells me that x equals 0 is one of my zeros. It has a multiplicity of 1 because it only appears once. Okay, the next factor I see is x minus 3. And if I solve that for x, set that equal to 0 and solve for x, I actually get 3. Because it is squared, that means its multiplicity is 2. And then finally, I have x plus 1 is one of my factors. If I set that equal to 0 and solve, I get negative 1. And this one has a multiplicity of 3. Now, the degree of the polynomial is adding all the multiplicities together. So the degree is 1 plus 2 plus 3, or 6. This is a 6th degree polynomial because 1 plus 2 plus 3 is equal to 6. Now let's graph it and take a look. So let's see, we have y equals 3x, parentheses, x minus 3, close parentheses, squared, and then parentheses, x plus 1, close parentheses, to the power of 3. So you can see it crosses the x-axis at negative 1 and 0. And also 3. Let me zoom. There it is here. Maybe I can squish it this way. It goes up. Kind of hard to tell what it does. But anyway, you can see where it crosses the x-axis. Now look at the interesting thing. At 0, it just crosses. Nothing crazy happens. It almost just looks like a straight line. Look what happens at 3. So 0 had a multiplicity of 1. It just goes straight through the graph. 3 has a multiplicity of 2. Notice it sort of bounces off the x-axis or is tangent, which we would expect when you have an even multiplicity. And then look what happens at x equals negative 1, where you have a multiplicity of 3. You have this inflection point where the graph sort of does this little squiggle. And you would expect that any higher odd degree, if it had a multiplicity of 5 or 7 or 9, it would be even flatter there where it crosses the x-axis. So let's make a note of these observations. So here at x equals 0, where the multiplicity is 1, it simply crosses the x-axis. Where the multiplicity of 2, it was tangent to the x-axis. It bounced off of the x-axis at x equals 3. And if you want, you can go to Desmos.com, pull up a graphing calculator, and you could explore this a little bit more for yourself if you like. The multiplicity of 3, it sort of flattens out a little bit at 0 there. It still crosses, but it does this little inflection thing where it kind of flattens out there. And again, the degree is 6. Now, I didn't say anything about end behavior, so let me go back and look at the end behavior of that graph. It looks like the ends are going to be both pointing up, and that makes sense to me since this is an even degreed function. It's degree 6, that's an even number, so we know both ends will point in the same direction, and the leading coefficient is positive, so that all adds up. All right, let's take a look at this next example. We have -2/5. That's not a variable, so we can ignore that. Let's go on to x plus 1. If we set that equal to 0 and solve, we get x equals -1. It has a multiplicity of 4 because of this. And then we have x minus 1. Set that equal to 0 and solve. Whoops, this first one should have been a -1. This one only has a multiplicity of 1. When there is no exponent, we understand it to be 1. And 4 plus 1 is 5, so this is a degree 5 polynomial. Since it's odd degreed, I'm going to expect the ends to do different things. So let's go take a look at the graph of this one. Y equals -2/5, -2 divided by 5. And then parentheses, x plus 1, to the power of 4. Excuse me. And then x minus 1. Boom. Okay. So look what happens at -1. It's kind of flat there, but it is tangent to the graph at -1, which we expect when you have an even multiplicity. And then at x equals 1, it just kind of crosses right through without anything fancy happening, which we expect when the multiplicity is 1. Notice the end behaviors are different. The left side is pointing up, the right side is pointing down. Since they are in opposite directions, we can look to the right side. It's pointing down, which is no surprise because the leading coefficient is -2/5. So that all checks out to what we know. So here at x equals -1, the multiplicity was 4. We found even though it was really flat, it's tangent to the graph there. And at x equals 1 with the multiplicity of 1, it simply crosses the x-axis there. And again, we get the degree by just adding 4 plus 1. Number 8 says write the expanded form of the polynomial p of x that has a 0 of 5 with a multiplicity of 1 and a 0 of -2 with a multiplicity of 2, and the leading coefficient is 1. Okay, so we're calling it p of x. Okay, I can do that. Leading coefficient is 1. Not that I needed to write that. One of the zeros is 5. That means the factor would be x minus 5. It has a multiplicity of 1, so it only appears once. We have a 0 of -2, So in the factor, it's going to look like x plus 2, and it has a multiplicity of 2. So we want to expand this. Now I want to remind you what this means. This means I don't need to write the 1. We have x minus 5, and because we have x plus 2 squared, it means x plus 2 times x plus 2. So I need to multiply these three binomials, but I can only multiply them 2 at a time. So I'm going to start with the two that are the same. I'm going to multiply x plus 2 times x plus 2. So I'm going to do x times x is x squared. X times 2 is 2x. 2 times x is 2x. And 2 times 2 is 4. So I have x minus 5. And then if I simplify all of this, I can combine 2x plus 2x and call that 4x. Now I still need to multiply x minus 5 times this trinomial. Now that's starting to get a little complicated for me. So sometimes if I have to do multiplying of polynomials like this, sometimes I like to organize myself in a bit of a matrix. So I'm going to separate this into a 2 by 3 matrix. I'm going to put x and minus 5 down the side. I'm going to put x squared plus 4x and plus 4 across the top. Now I'm going to treat this like a Punnett square from biology, where you have the mama with the brown eyes and the daddy with the blue eyes, and you try to figure out what possible combinations the baby's going to have. You just do the, maybe you don't remember that from biology, but this always reminds me of that. Basically, you're just going to multiply the rows and the columns together. So in this first box, you're multiplying x squared times x. So x squared times x, which is x to the 3rd power. And then keep moving with this x times 4x would give you 4x squared. And then x times 4 is 4x. Now in this row, we're multiplying negative 5 times x squared, which is negative 5x squared. Negative 5 times 4x would be negative 20x. And negative 5 times 4 is negative 20. So I have my answer. I need to simplify it a little bit. I've got my x cubed. But my x squareds, I have 2 boxes with x squared. I can combine these. Minus 5x squared and plus 4x squared makes minus 1x squared. I can combine these x's. Minus 20x and plus 4x is minus 16x. And then finally, minus 20. And that's my simplified polynomial. In expanded form, or you might say in standard form. All right, we're getting there. It says find the equation of the polynomial given that the multiplicity of each zero is less than or equal to 4 and the y-intercept is 0, negative 13.5. Okay, so let's see. So this one right here appears to be a multiplicity of 2. This one right here appears to be a multiplicity of 3 because it does that inflection thing. So at negative 1, it bounces off. At 3, it sort of inflects. Okay, and what else? They told me that this point right here, whoops, crosses the y-axis at 0, negative 13.5. So that could be useful as well in a moment. So let me come down here and use the space. So let's see, what do I know? I know that we have x equals negative 1, and the multiplicity is 2 because it bounces off. And I have x equals 3 with a multiplicity of 3 because of the way it behaves, how it does this inflection thing. So I know my function, I don't know what a is, but I'll figure that out in a minute. From x equals -1, my factor is going to be x plus 1, and the multiplicity of 2 means that's going to be squared. From my x equals 3, the factor is going to be x minus 3, and it has a multiplicity of 3, so I cube it. Now, I'm not going to expand that because this would just take a lot of time, but I do want to find my a value. What I do know is this point right here. I know that if x is 0, my answer is -13.5. So I'm going to take my function, I'm going to substitute 0 in place of x, and I'm going to say that's equal to -13.5, and this is going to help me find my a value. Now 0 plus 1 is 1, and 1 squared is 1. 0 minus 3 is -3, and -3 cubed is -27. So a times 1 times -27 is -27a. And if I divide both sides by -27, I am going to get 1/2. So going back, I'm going to take that and substitute that in here. So my function is, all the hardest work was just figuring out a. 1/2 times x plus 1 squared times x minus 3 cubed. Boom. Number 10, I'm going to sketch this polynomial by hand. Okay? Then I'm going to use Desmos to compare and see how I've done. So let me give myself a little sketch grid to sketch on. And let's see what I've got. So I'm starting out with this one, x equals 0, has a multiplicity of 1. So it's going to cross at 0. It's just going to cross right on through. Then I've got x minus 1 as a factor. And that means x equals 1 is my 0. So I'm going to come over here to 1. And I put a 0 here. This one has a multiplicity of 3. So I know it's going to do some kind of weird inflection thing there. Let's see, what's next? I have x minus 3. So I already did that one. X minus 3. So my 0 is x equals positive 3. This one just has a multiplicity of 1. So 1, 2, 3. And then I've got x plus 2. If I set that equal to 0 and solve, I get -2. This one has a multiplicity of 2. Okay, because of this. So let me go back to -1, -2. Now, the leading coefficient is a positive 1. So I know the right end is going to point up. I know it's just going to cross at x equals 3 because the multiplicity is 1. But so it's just going to cross over uneventful. At 1, though, it kind of does this inflection thing. And then it crosses at 1. And then at 2, it is tangent, so it kind of does this weird thing here. Now, I realize that is not very pretty. In fact, the worst part is this in here. Whoops. Let me see if I can do that a little bit better. So, I'm going to do that a little bit better. So here's what it's going to look like. It's going to kind of come up through here. It's going to come up here. It's going to inflect. Okay, I don't know that that's any better. I don't know how low or high it goes, but I know here it's just going to be tangent. Yeah, I really don't like the way I've drawn that at all. I'm going to try that one more time. So it is going to be tangent at -2. Bounce off. It's going to cross here. It's going to inflect here. It's not a very good inflection. And then it's going to just go through here. All right, not pretty. Let's go to the experts at Desmos and let them do this for me a little bit nicer. Y equals, what did we have? We had an x, and then we had an x minus 1 to the power of 3. Then we had an x minus 3 in parentheses. We had to the power of 1, so I don't need to write that. And then x plus 2 to the power of 2. All right, so much better, much better. Okay, we can see it bounces off at -2, it crosses at 0, it inflects at 1, and crosses at 3. Yes, thank you, Desmos. Beautifully done. All right, my goodness. Long notes today. Number 11 says use the rational zeros test to find a zero and completely factor the polynomial. So here, what I'm going to do is look at my p's and q's. So p's come from this number, okay? The factors of 9. The factors of 9 are plus or minus 1, plus or minus 3, and plus or minus 9. Those are the only numbers that divide evenly into 9. My q's come from the leading coefficient. My q's are the factors of 2, plus or minus 1, plus or minus 2. So my p's over q's are going to be all of the possible combinations of the p's divided by the q's. So I do this very systematically. I'm going to start with the 1. 1 over 1 is 1. 1 over 2 is 1/2. Now I'm moving on to the 3. I'm going to do the same thing. 3 over 1 is 3. And 3 over 2 is 3/2. Or you might say 1.5. On to 9. 9 over 1 is 9, and 9 over 2 is 9/2. So we have 1, 2, 3, 4, 5, 6, 12 different numbers to choose from. 6 positives, 6 negatives. So these are all the numbers that could possibly be zeros. So we could test them out. The way you could test them out is you could do synthetic division, or you can simply substitute these numbers until you find the ones that equal 0. Okay? So, for example, if I'm just going to go to my scientific calculator this time. So if I started with 1, if I substitute 1, let's see, to the power of 4, 2 times x to the power of 4, plus x, so I'm substituting 1 for x, to the power of 3, minus 19x squared, substituting 1, plus 9. That does not equal 0. So you can eliminate 1 from the list. 1 is not a possibility. So then I'm going to try -1. So I can just go back in here and alter this and change the 1s to -1s. Guess what? Negative 1 does not equal 0. Whoops, I messed up. It's 2x to the 4th plus x to the 3rd minus 19x squared. I forgot the minus 9. Minus 9x. Okay, I knew that was a mistake because that was supposed to be 0. So negative 1 is a 0 because when you substitute negative 1, you get a 0. So remember that. I'm going to next try a half. Now remember, there's as many as 4, all right? As many as 4, because this is an x to the 4th. So once I find 4, I'm done. I've already found 1. I need to find 3 more. So let me move on to a half. So again, I'm just going to alter this. I'm going to call a half 0.5 because I think it'll be faster to enter. 0.5. 0.5. Well, what do you know? I have already found 2 of the 4. I found that negative 1 worked, and I found that positive 1/2 worked. Let's try negative 1/2, negative 0.5. So I've got negative 1 and positive 1/2 so far. So you have to try the positive and negative of every one. Negative 0.5 does not equal 0, so it's not a 0. Let's move on to 3. So again, I'm just going to change plugging in 3. Woohoo! I have now found 3 zeros. One of the zeros was negative 1. One of them was positive 1/2. One of them is positive 3. Let's try negative 3. Yay! Love it. So there were 12 numbers to try. We didn't have to try all of them. I've already found 4 zeros, and I know that there won't be any more than 4 since this is an x to the 4th. Okay, so the ones that worked were x equals, the first one I found was negative 1. The next one I found was a half. The next one I found was 3, and then also negative 3. And again, that's 4. I know that's all there is because of that. Now, let me just warn you, you could try all of these numbers and not find your 4. That would simply mean that either some of these have a multiplicity of more than 1, or that maybe you have some complex or irrational zeros. But if the numbers are rational, you'll get this. Now that we know these zeros, we can write the factored polynomial. So if I write the factors, I'll add 1 to each side here. So there's one factor. Remember, I don't want fractions in my factors. So this next one, I'm going to multiply both sides by 2. That'll give me 2x equals 1, or 2x minus 1 equals 0. Subtract 3. Add 3. All right, so here we go. My function is x plus 1 and 2x minus 1 and x minus 3 and x plus 3 in any order that you like. And I see this 2 here and this 2 here, so I know that that's going to work out lovely. Number 12, given a 0 of the polynomial, determine all other zeros and write the polynomial in terms of a product of linear factors. Okay, so for this one, I'm going to need to do synthetic division. So my 0 is 3. So I'm going to take my 0, and actually what I'm going to be doing is I'm actually going to be dividing this whole thing by the factor x minus 3. And here's how you do it. So you take your 3, kind of box it in over here. And now you're going to write down your leading coefficients. So I see that there is a 1x to the third power, then a 3x squared, then a minus 10x to the first power, and then a minus 24 constant. You want to make sure these are in order, highest power of x on down, and make sure that you're not skipping any. For example, if there wasn't an x squared term, you would put a 0 to indicate that in the place of the 3. Okay. Skip a line and draw a line. The first number comes straight down, and then you are going to multiply. So you're going to do 3 times 1 is 3. Put that number here. And then you're going to add straight down. 3 plus 3 is 6. And you're going to repeat that process. 3 times 6 is 18. Put that number here. Add. Negative 10 plus 8 is positive 8. Repeat. 3 times 8 is 24. Add. Negative 24 plus 24 is 0. So these 3 numbers represent what you get when you divide this. Now, since this one started with an x to the third power, this one starts with an x to the second power. 1x to the second power plus 6x to the first power plus 8 is your constant. Now, this is something you can factor quite easily. Looking for 2 numbers that multiply to be 8, that add to be 6, is 4 and 2. So you now have found your other 2 factors for p of x. We were told at the beginning that one of the factors was x minus 3. When we divided it, we found the other 2 factors are x plus 4 and x plus 2. I know there are only 3 factors because this is an x cubed, x to the third power. Let's try that again. So I know one of the zeros is negative 1/3. Now, let's talk about what that factor is. If you say x equals negative 1/3 is your 0, I'm going to multiply both sides by 3. That'll give me 3x equals negative 1. And then I'll add 1 to each side. So the factor is actually this. So what I'm going to do is take this and divide it by this factor and figure out what the rest of my zeros are. So remember that factor, but I'm actually going to use this negative 1/3 in my synthetic division. So put that number in the corner. This is nice and in descending order, so put all your coefficients. 3, negative 14, 7, 4. And I kind of space them out a little bit. Skip a line, draw a line. Bring the first number straight down. Now we multiply. Negative 1/3 times 3 is negative 1. You're going to add negative 14 plus negative 1 is negative 15. Repeat. Negative 1/3 times negative 15 is positive 5. Put that number here. Add. 7 plus 5 is 12. One more time. Negative 1/3 times 12 is negative 4. Put that number here and add. And of course, you're going to get 0 every time when you've used what you already know is a 0. So take these remaining numbers. Since we started with an x to the third, this is going to start with 1 less, x to the second, minus 15x plus 12. Now I can factor this. First, I'll factor out a 3, since 3 is a common factor to all 3 terms. Then I can factor this even further. 2 things that multiply to be positive 4 that add to be negative 5 are negative 4 and negative 1. So my factors are, I have 3x plus 1. I already was told that was a factor. Okay. Now, you can ignore this 3. I've already got that taken care of here, and I don't need anything bigger than a 3. I've got x minus 4 and x minus 1. All right, in C, we have our polynomial function. One of the zeros is 3i. Now remember, we said that complex zeros always appear in pairs. You can think of 3i as 0 plus 3i. We know that also 0 minus 3i will be a 0 because they always appear in complex conjugate pairs. So I know that x equals 3i is a 0 and x equals negative 3i is a 0. Okay, I am going to start by multiplying. Well, first I'll subtract 3i so that I can set this equal to 0. I will multiply these together. And let's see what that happens here. So let's see, x times x is x squared. X times 3i is 3xi. Negative 3i times x is negative 3xi. And negative 3i times positive 3i is negative 9i squared. So the positive 3xi and the minus 3xi cancel. So I have x squared minus 9 times I squared. But remember, I squared is negative 1. So this turns into x squared plus 9 as one of my factors. Now, to find the other zeros, I'm going to cheat and I'm going to go to the graph. So let me go here. All right, this is a little too complicated. This one is a little too complicated without the help of a graph. So let's see, I have y equals x to the power of 4 minus x cubed plus 7x squared minus 9x minus 18. All right, I see that it crosses the x-axis at negative 1 and positive 2. Okay, that's very, very helpful. So I know that x equals negative 1 and x equals positive 2 are two other factors. And I know that's all of the 4 factors because this is an x to the 4th. So let's see, if I add 1 to each side, one of my factors is x plus 1. If I subtract 2. So now that I know one of my factors, or I should say, when you have this, it simplifies to x squared plus 9. My other factors are x plus 1 and x minus 2. So for complex conjugates, you will multiply those together, and what happens is the i's go away when you do that. So you won't find that in your final answer. Okay, this is the lesson that never ends. Let's look at this one. I have this polynomial function, and I have one of the zeros as 1 minus 2i. So this is going to be similar. So I know the other one is 1 plus 2i. So let me go ahead, let's see. So x equals 1 minus 2i, and x equals 1 plus 2i. If I get that equal to 0, I'm going to have to subtract 1 and add 2i for that one. And for this one, I'm going to subtract 1 and subtract 2i so that it says equals 0. So now I kind of have a mess. I have to multiply this times this. Those are trinomials. I'm going to need a little help. I'm going to make a 3 by 3 matrix to help me multiply these. Just to keep me organized so that I don't mess up. So down the side, I'm going to put this first one, x minus 1 plus 2i. And the second one across the top, x minus 1 minus 2i. And I'm going to multiply every row and column together. So x times x is x squared. X times negative 1 is negative x. X times negative 2i is negative 2xi. X times negative 1 is negative x. Negative 1 times negative 1 is positive 1. Negative 1 times negative 2i is positive 2i. X times positive 2i is positive 2xi. 2i times negative 1 is negative 2i. And 2i times negative 2i is negative 4i squared. Now, I see some things that cancel. For example, a positive 2xi and a negative 2xi cancel. And a negative 2i and a positive 2i cancel. So what I have left is an x squared. I can combine these two. Minus x and minus x makes minus 2x. I have a positive 1. And I have a minus 4i squared. But remember, I squared is negative 1. So this is going to turn into a plus, a positive. So I've got x squared minus 2x plus 1 plus 4 times 1 is 4. So this is plus 5. So all of that to find what you get when you multiply these two complex ones. Once again, I'm going to use my calculator just to help me find those other zeros a little bit quicker. So y equals x to the 4th minus 4x cubed plus x squared plus 6x minus 40. All right, so I see, again, the complex ones don't show up on the graph like these do. So we've got a negative 2 and a positive 4. So unless they told us, I really wouldn't have any way of knowing exactly what those are. So I've got negative 2 and positive 4 as my other two zeros. So x equals negative 2 and x equals positive 4. And again, I know that there are going to be 4 because it's x to the 4th power. I was given one of the complex numbers. I know the other one has to also be. So then I'm adding 2 to each side, subtracting 4. So all the hard work is done. So I'm taking this x squared minus 2x plus 5, which by the way does not factor anymore. And then my other two factors, x plus 2 and x minus 4. Whew. And finally, are we on our last one yet? Last page, maybe. Okay, this one has a 0 of 1 with a multiplicity of 2. Okay, this is a good one. So that means x equals 1 if I subtract 1 from each side. What that means is this polynomial function has x minus 1 squared, so twice. And then it's going to have 2 more, I don't know what. So let's see, how could I find the others? If I go and graph it, let's see what I can do. Let's take a look at the graph. Just going to try to alter this one. Plus 4 and then minus 2. Minus 12x, and then plus 9. Notice its tangent at negative 3 and 1. It bounces off of the graph. That means I have two zeros with multiplicities of 2. Negative 3 and 1. So negative 3 was another one if I add 3 to each side. So this is another one that appears twice. Now, I probably wouldn't write it like that. I would probably write it like this: x minus 1 squared and x plus 3 squared. And 2 plus 2 is 4, just as expected. Okay. All right. Let's look at solving a polynomial equation. So a good way to start is going to be to graph it. I know that this has an x to the third, so I know there's at most 3 solutions, or 3 real solutions. There are definitely 3 solutions. So y equals x to the power of 3 plus 6x squared plus 11x plus 6. It crosses the x-axis 3 times. So at negative 3, negative 2, and negative 1. Spread this out a little bit. Negative 3, negative 2, positive, negative 1. Boom. I expected 3 answers. There they are. So I can get this definitely from the graph. So let me go back here. So my solutions are negative 3, negative 2, whoops, negative 1. Did I do that right? X cubed plus this is under. Yes, very nice. Okay, let's take a look at this next one. Again, I'm going to try graphing until it doesn't work anymore. So for this one, I've got y equals 12x cubed. 12x to the power of 3 minus 13x squared plus 2x minus 1. All right, I expect 3 solutions, but it only crosses the x-axis once, so I'm going to have to use some other math to help me find the other solutions. So the only real solution is positive 1. Okay, so x equals 1 is a solution, but there are 2 more. This is an x to the third. So I am going to divide this by the factor x minus 1. And I do that with synthetic division. So I put a 1 in the box. I put the coefficients. I don't know why I put a plus sign there. We know it's positive if you don't put a negative. All right, everything's in order. Bring down the 12. Multiply 1 times 12 is 12. Add negative 13 plus 12 is negative 1. 1 times negative 1 is negative 1. Add 2 plus negative 1 is 1. 1 times 1 is 1. And add negative 1 plus 1 is 0. So you expect that, but I just needed to do that to get these numbers. Start 1 less than your power of 3 on your x, 12x squared minus 1x plus 1. Now, you would factor that if you can, but that is not factorable. So I'm going to have to use the quadratic formula to help me to find the other solutions. So let's see. A is 12, B is negative 1, C is positive 1. The quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So if I plug in those numbers, a, b, and c, I've got the negative of negative 1 plus or minus the square root of b squared, so negative 1 squared minus 4 times a times c all over 2 times a. So let's see, that's going to be a positive 1 because a negative of a negative is a positive. Negative 1 squared is positive 1 minus 4 times 12 times 1 is 48. All over 2 times 12 is 24. So let's see, 1 minus 48 is negative 47. This is why you didn't see where it crossed the x-axis, because when you take the square root of a negative number, guess what? I comes into the picture. I don't know what the square root of 47 is. That's a prime number. So my other two solutions come from this. We've got 1 over 24 plus square root of 47 over 24i, and 1 over 24 minus square root of 47 over 24i. So my three answers were 1, I was told that in the beginning, that 1, well, I found 1 to be one of the solutions from the graph, and then these are the other solutions here. Ugh. So the point of that example is this. Sometimes when you graph, you're not going to see all of your solutions. You're only going to see your real solutions. So you can use your real solution, use synthetic division, and then from there, find your complex solutions. Now C is going to be easy. It's going to be just like the one we did last part A, because this one will give us a nice answer. So we got, let's see, y equals x to the power of 3 minus 7x squared minus x plus 7. I expect 3 solutions. Scrolled too weird, didn't I? Here we go. I expect 3 solutions, and guess what? I've got 3 solutions. I don't know why that's so weird like that. My solutions are -1, +1, +7. It just can't get any more beautiful than that. So, here, x equals -1, +1, and 7. And we are way past our time, I am certain. We are going to skip the last example. It is absolutely not necessary. You may have to revisit this video. There is a lot of information in here. So I suggest you just keep these examples handy while you are working through the homework and the quiz. And try to find a problem here that we've done together similar to the problem that you're working on. And of course, as always, if you need help with any of it, please reach out. Thanks so much.